In this video, let's look at the periodic trends for ionization energy. So for this period, as we go across from lithium all the way over to neon, so as we go this way across our periodic table, we can see in general there's an increase in the ionization energy. So lithium is positive 520 kilojoules per mole, beryllium goes up to 900 kilojoules per mole, and then again in general we see this increase in ionization energies going over to neon. So going across a period is an increase in the ionization energy. And that's because as we go across our period, there's an increase in the effective nuclear charge, so increase in Z effective. And remember, the formula for that is the effective nuclear charge is equal to the actual number of protons, which is Z, and from that we subtract S, which is the average number of inner electrons shielding our outer electrons. So let's examine this in more detail, looking at lithium and beryllium. Lithium has atomic number 3, so 3 protons in the nucleus, so a positive 3 charge. And lithium's electron configuration, we know, is 1s2, 2s1. So 2 electrons in our 1s orbital, and 1 electron in the 2s orbital. Beryllium has 1 more proton and 1 more electron. So 1 more proton in the nucleus, so a plus 4 charge. And for beryllium, the electron configuration is 1s2, 2s2. So 2 electrons in the 1s orbital, and then 2 electrons in the 2s orbital. Let's calculate the effective nuclear charge for both of these. And first we'll start with lithium. So for lithium has a plus 3 charge in the nucleus. So the effective nuclear charge is equal to positive 3. And from that we subtract the average number of inner electrons shielding our outer electrons. In this case, we have these 2 inner or core electrons that are shielding our outer electron, our valence electron, from this full positive 3 charge. So we know that like charges repel, so this electron is going to repel this electron a little bit, and this electron repels this electron. And these 2 inner core electrons of lithium have a shielding effect. They protect the outer electron from the full positive 3 charge. So there's 2 shielding electrons, so for a quick effective nuclear charge calculation, positive 3 minus 2 gives us a value of plus 1 for the effective nuclear charge. So it's like this outer electron of lithium is feeling a nuclear charge of plus 1, which pulls it toward the nucleus, right? So there's an attractive force between the outer electron and our nucleus. Now the actual calculation for this, S I should say, does not have to be an integer, and the actual value for lithium is approximately 1.3, but our quick crude calculation tells us positive 1. Let's do the same calculation for beryllium. So the effective nuclear charge for beryllium is equal to the number of protons, right, which for beryllium is positive 4. And from that, we subtract the number of inner electrons that are shielding the outer electrons. So it's a similar situation. We have 2 inner electrons that are shielding this outer electron, right? They're repelling this outer electron, shielding the outer electron from the full positive 4 charge of the nucleus. So we say there are 2 inner electrons, so the effective nuclear charge is positive 4 minus 2, giving us an effective nuclear charge of positive 2. In reality, the effective nuclear charge is approximately 1.9, and that's because beryllium has another electron in its 2s orbital over here, which does affect this electron a little bit. It repels it a little bit, and so it actually decreases the effective nuclear charge to about 1.9. But again, for a quick calculation, positive 2 works. So the outer electron for beryllium, let's just choose this one again, is feeling an effective nuclear charge of positive 2, which means that it's going to be pulled closer to the nucleus. There's a greater attractive force on this outer electron for beryllium as compared to this outer electron for lithium. The effective nuclear charge is only plus 1 for this outer electron. And because of this, the beryllium atom is smaller, right? The 2s orbital gets smaller, and the atom itself is smaller. Beryllium is smaller than lithium. So this outer electron here, let me switch colors again. This outer electron for beryllium is closer to the nucleus than the outer electron for lithium. It feels a greater attractive force, and therefore it takes more energy to pull this electron away from the neutral beryllium atom. And that's the reason for the higher ionization energy. So beryllium has an ionization energy of positive 900 kilojoules per mole, compared to lithium's of 520 kilojoules per mole. So it has to do with the effective nuclear charge. So far, we've compared lithium and beryllium, and we saw that the ionization energy went from positive 520 kilojoules per mole to 900 kilojoules per mole. And we said that was because of the increased effective nuclear charge for beryllium. But as we go from beryllium to boron, there's still an increased effective nuclear charge, but notice our ionization energy goes from 900 kilojoules per mole for beryllium to only 800 kilojoules per mole for boron. So there's a slight decrease in the ionization energy. And let's look at the electron configuration of boron to see if we can explain that. Boron has 5 electrons, so the electron configuration is 1s2, 2s2, and 2p1. So that 5th electron of boron goes into a 2p orbital. And the 2p orbital is higher in energy than a 2s orbital, which means the electron in the 2p orbital is on average further away from the nucleus than the 2 electrons in the 2s orbital. So if we just sketch this out really quickly, let's say that's my 2s orbital. I have 2 electrons in there. And this 1 electron in the 2p orbital is on average further away from the nucleus. So those 2 electrons in the 2s orbital actually can repel this electron in the 2p orbital. So there's a little bit extra shielding there of the 2p electron from the full attraction of the nucleus, right? So even though we have 5 protons in the nucleus and a positive 5 charge for boron, the fact that these 2s electrons add a little bit of extra shielding means it's easier to pull this electron away. So it turns out to be a little bit easier to pull this electron, the 2p orbital, away due to these 2s electrons. And that's the reason for this slight decrease in ionization energy. As we go from boron to carbon, we see an increase in ionization energy. From carbon to nitrogen, an increase in ionization energy. Again, we attribute that to increased effective nuclear charge. But when we go from nitrogen to oxygen, we see a slight decrease again, from about 1,400 kilojoules per mole down to about 1,300 kilojoules per mole for oxygen. So let's see if we can explain that by writing out some electron configurations for nitrogen and oxygen. Nitrogen has 7 electrons to think about, so its electron configuration is 1s2, 2s2, and 2p3. So that takes care of all 7 electrons. For oxygen, we have another electron, so 1s2, 2s2, 2p4 is the electron configuration for oxygen. Let's just draw, using orbital notation, the 2s orbital and the 2p orbitals. So for nitrogen, here's our 2s orbital. We have 2 electrons in there, so let's draw in our 2 electrons. And for our 2p orbitals, we have 3 electrons. So here are the 2p orbitals. And let's draw in our 3 electrons using orbital notation. Let's do the same thing for oxygen. So there's the 2s orbital for oxygen, which is full, so we'll sketch in those 2 electrons. And we have 4 electrons in the 2p orbitals. So let me draw in the 2p orbitals. There's 1 electron, there's 2, there's 3. And notice what happens when we add the 4th electron. We're adding it to an orbital that already has an electron in it. So when I add that 4th electron to the 2p orbital, it's repelled by the electron that's already there, which means it's easier to remove one of those electrons. So electrons have like charges, and like charges repel. And so that's the reason for this slight decrease in ionization energy. So it turns out to be a little bit easier to remove an electron from an oxygen atom than nitrogen due to this repulsion in this 2p orbital. From there on, we see our general trend again. The ionization energy for fluorine is up to 1681, and then again for neon, we see an increase in the ionization energy due to the increased effective nuclear charge.